experimental infrastructure towards ubiquitously safe robotics systems using RobMoSys. The ITIS building blocks integrate existing technologies from the RobMoSys PRC2 platform for robot controller construction, and a mass, architecture-driven, multi-concern and seamless assurance and certification of cyber-physical systems projects. PRC2 will provide a framework for the functional design of the robot controller with component development and system configuration views. It will additionally provide tools for code generation from these views. AMAS will provide the meta-modeling backbone for safety validation by providing a safety modeling view for both model-based safety analyses and simulation-based fault injection. Two remarkable challenges exist when developing reusable safe robotics systems and software. First, modular and role-based design needs to be provided. Second, solutions for an early safety assessment are needed, which stands for combining model-based safety analysis and robustness simulation by means of fault injection. Some of the most attractive benefits of applying the ITIS methodology are the development of composable, replaceable and reusable safe components. Robotics systems face hazards whose sources belong to software, electronic, electric or mechanical parts of the system itself, as well as to human errors, or to an uncertain and stressful environment. Functional safety is the aspect of safety that aims to avoid unacceptable risks due to electric malfunctions. The system should be designed to properly handle likely human errors, hardware and software failures and operational, environmental stress. The RobMoSys project defines structures which enable the management of the interfaces between different robotics-related domains, levels of abstraction and roles. ITIS will broaden the ecosystem by considering safety aspects such as the development of a safety view and the introduction of a new role called safety engineer. The safety analysis and validation steps are fundamental aspects to perform the safety assessment. Some of the commonly used risk assessment methods are preliminary hazard analysis, hazard operability analysis, failure modes and effects analysis and fault tree analysis. Furthermore, fault injection simulations complete these analyses by finding unexpected hazards, fault forecasting, and verifying the implemented safety mechanisms. Fault injection is a common technique for validating the effectiveness of fault tolerance mechanisms by studying the behavior of the system in presence of faults. The effects of software or hardware faults are emulated by randomly changing code or data at different software locations. The ITIS framework sets up, configures, executes and analyzes the simulation results. Model-based design combined with a simulation-based fault injection technique and a virtual robot poses as a promising solution for an early safety assessment of robotics systems. The added value of including robots and environment models is that the maximum time before the robot dynamics are unsafely affected can be identified. In other words, it allows quantitatively estimating the relationship of an individual failure to the degree of misbehavior on robot level. The ITIS approach is explained by using a real-time Cartesian impedance control system, in talk mode as a use case scenario. The ITIS overall approach is as follows. Before starting the fault injection experiments, the golden system model, which represents a model without any faults in place, and its corresponding simulations must be created. A component supplier manages the design and configuration of components and their parameters. A system builder designs the global architecture by assembling components and adjusting settings. After, the controller code is generated, and the simulations run in Gazebo. Once the components and the system are designed, the safety engineer starts the FMEA process, which can be performed in a compositional way. First, FMEAs are carried out at component level. Then, The FMEA is developed at system level and the safety requirements are defined. The failure modes set during this process will be represented as fault models in the configuration of the faulty system. In order to prevent a failure mode, a preventive action or safety requirement is defined by the safety engineer. These safety requirements will be the basis for the pass-fail criteria of the fault injection experiments. After performing the traditional model-based safety analysis, fault injection experiments can be specifically set up to redefine and validate the aforementioned FMEA. The safety engineer starts by selecting the system model and the robotics scenario, which includes the operational situation and the robot. After that, it is important to define the fault injection policy, which is referred to as the fault list. The fault list is used to produce a faulty model only in terms of reproducible and prearranged fault models. Fault models are characterized by a type, for example, emission, frozen, delay, invert, oscillation or random, target location, injection triggering, time-driven, and duration. The original system model is modified though the fault injector script according to the fault list. Out of these faulty models the deployed code is generated, and the simulations are run. The results of the fault injection experiments can be visually seen in the gazebo simulation environment or in the fault injection simulation results view. The safety engineer analyzes the resulting simulation traces in the simulation results view, which illustrates the main comparison between golden and faulty signals. This safety validation process consists of evaluating what fault models violate the established safety requirement. In other words, the pass-fail criteria are established upon the predefined safety requirements. When a safety requirement is violated, the safety architecture refinement process is accomplished and the necessary safety mechanisms included.